Okay, in 7.2 here, we're going to look at some example problems of growth and decay. So continuously compounded interest is an example of a growth function, and that function uses this formula, a equals p times e to the RT power. So let's define what the parts of this are. P represents your principal in the interest problem, and that's the amount of money that you're depositing in the bank or the amount of money that you're borrowing from the bank. E is going to be an actual number. It's approximately 2.71828. It keeps going. And that's similar to the number pi, where pi is approximately 3.14159. E is going to be a number we're going to be using a lot here in the days to come. Then we have R, which represents your interest rate as a decimal. So make sure we convert that to a decimal. Okay. And then T represents your time. Okay. So on this particular problem, if we just plug into the formula, we have $600 going into the bank for 5 years at 8% interest, compounded continuously, meaning we're just using this particular formula here. So your final amount's going to equal 600 times E, and I'll show you where E is on the calculator here in a second, to the power of your interest rate, which is 0.08, since it's 8%, times T, and your T is time, which in this case is 5 years. So now let's look at how we plug this into the calculator. So on your calculator, first of all, on your calculator, let me lift this off for a second, you will see on your LN button here, right above, dizzy yet? You have a key, and it says e to the x right there. It's on the LN key right there, e to the x. Okay. So on that key, you are going to use that to get your expression in here. So we're going to type 600, then you're going to hit second, and the LN key, which again is just to the left of the number 4 key. It's on the second function. So that's e to the power, and then in there we want to do the power of 0.08 times 5. So this is 0.08 times 5. Then you're going to close your parentheses. So here, make sure you have 600 e to the power, and then in parentheses 0.08 times 5. Hit enter, and there's your dollar amount, $895. So this is approximately $895.09 to the nearest penny. Since it's money, we'll go to the nearest penny. Okay? So let's try another one. Number 2, we have our principal, which in this case is 200, times e to the power. Now here our interest rate is 0.07, and then this is going to go in for 40 years. Okay. So on this one, let's clear this out. We've got $200, second function, ln, to get to e to the power, and then this is 0.07 times 40 years, close parentheses, and there is our dollar amount, approximately $3,288.93. Okay. The next two problems are examples of decay functions. So here our multipliers needs to be smaller than 1. So in this example, you'll see our multiplier, we're multiplying it by e, and e was approximately 2.71828, so obviously that was bigger than 1. So here our multiplier's got to be smaller than 1 if it's a decay function. And these are what we call half-life problems, and in a half-life, A half-life is how long a period of time does it take for half of something to disappear. Okay, so if we just look at a case, if we had 100 of something, and we said half of it's going to disappear every 24 hours, well, after the first day goes by, your 100 would turn into 50. After a second day goes by, your 50 would turn into 25. After another day goes by, that 25 would turn into 12.5. And it would keep going down and down and down by half every single day. Okay? So what we want to do is we want to write a decay function. So here we're going to write it in exponential form. So y equals a times b to the x. So a represents your initial amount, which in this case, your initial amount in this problem, we have 10 milligrams of this drug, HG197. This is a drug that's used for kidney scans. So your initial amount is 10 milligrams. And since we're doing half-lives, and we're taking a half each time, our multiplier is 0.5, or a half. And then that's going to be raised to the x power, and this is x going to be the number of half-lives. So on this particular problem, we need to figure out how many half-lives do we have. So we're going to have 10 times 0.5. Now, the half-life on this particular problem says it takes 64.1 hours for half of it to disappear. Well, we've only gone 48 hours so far. So since this number is smaller than 64.1, we haven't even had a half-life yet. This would need to be 64.1 for our power here to be 1. That would be 1 half-life. So instead, we have a fraction of half-life. So this is going to be 48 over the 64.1. The top number here represents the actual time passed. That's the actual time passed. And the bottom number in your power represents the half-life time. That's the half-life time. So if we plug that into our calculator, let's put that here, clear this out, we have 10 times 0.5 to the power. Now here we're going to need to divide 48 divided by 64.1. And all of that needs to go in parentheses. You need to take the half-life calculation and put that in parentheses because that whole calculation is your power. So we hit enter and we get our answer here is approximately 5.95 milligrams left over. So if you think about it, we haven't had a whole half-life yet, so this is less than a half-life. And if we actually had one half-life, we would have half of the 10 left. Half of 10 would have been 5, and we would have been left with 5 milligrams. But because we haven't had a full half-life happen yet, we're a little bit short of a half-life. We're going to be a little bit short of getting rid of half of the substance. So you can see we're just around 6. Okay. So let's look at one last example here on this. So on this one, we've got y equals, we start off with 5 milligrams this time. We're still doing a half-life, so it's 0.5. And now we have to figure out what our actual time is that's gone by. So this is after 2 days. 2 days have passed, so that's going to be 2. And our half-life time on this one is 8.04. So now let's see what that works out to be. So pop that in. We have 5 times 0.5 to the power of 2 divided by 8.04. And we get 4.21 milligrams. And if you look, we have only really gone, what is that, like 1/4 of a half-life. So we have not had very much of a half-life go by, so we should be very close to the original 5, which we are. Okay? So those are examples of growth and decay functions.